Now we start with the concept of diagonalization. In this we will study introduction to diagonalizations, mathematical analysis, role of Vander Monde matrix and example. Now about introduction to diagonalizations. In actual practice, we want to design a system in such a manner that we should get a desired performance. So, if you having an original model, in that case sometimes it is difficult to analyze that system, even sometimes difficult to design a controller, or internal property of the system cannot be easily studied. Therefore, we need to transfer a system into different form in such a manner that their properties should not change. So, here we are doing the same thing. Diagonalization means the same thing, that we have one system and it has been converted to another form, and that form is very much useful for control system applications. So, here the concept of diagonalization, this approach is method of transforming a general state space model into canonical form. It is also called as diagonal form because the system matrix A will be in a diagonal form after transformation. That is, the original model A is some one form. After transformation, it has been converted into diagonal form. That diagonal form is, we have only diagonal elements, remaining elements are zeros. So, how they are useful? So, it is useful for investigation of system properties, it is useful for evaluation of time response, it is useful in checking controllability and observability, and finally control design, and last it is useful in model order reduction techniques. Now, we will see the mathematical analysis. Here in state space, we have always start with the state space model. The state space model is represented by x dot equal to ax plus bu and y equals to cx plus du. Now, here is a problem. A matrix, it is in general form. There are many elements are involved in A matrix. So, our purpose is that A must be converted into diagonal form. So, x is the state vector. Now, what we want here? We want to convert this state vector into new vector. So, this is possible. So, we assume that A is non-diagonal and we defined a new state vector k in such a manner that, so we can write x equals to say m into k. Now, what happened? We have x is the original state vector, this k is additional vector, new vector we have taken, and m is the some matrix, model matrix. So, here m is operated on k, we got x, but now here we know x. So, now in this case this m is nothing but n cross n matrix. So, after this we can write down this equation as k equal to m inverse x. So, what we want? We want state vector in terms of k. So, what we can do? We can take k dot equal to m inverse x dot. Now, after this we can replace x dot equals to ax plus bu in this equation. So, you will get m inverse x dot equal to ax plus bu, and after solving this we will get m inverse ax plus m inverse bu. So, here we have equation in terms of k. Here we got m inverse a x, m inverse bu. So, here k, here is x. So, I think we have to change it because we want a complete equation in terms of k, because k is a new state vector. Therefore, what we can do? We can write k dot equals to m inverse a. What is x? X equals to mk, m inverse bu, and we can write down as m inverse m k plus m inverse b into u. And now this can be written as k dot equals to e bar k plus minus b bar into u. Now we have got equation which is in terms of k dot, earlier it is in terms of x. Now here a bar equals to m inverse m and b bar equals to m inverse b, and so if you determine this model matrix by determining different eigenvectors and make inverse, then multiply am, so you will find that this m inverse am and this a have same eigenvalues. Same eigenvalues means that they have same properties. So once we got k dot, now we can see about y, output y equals to cx plus du, and what is x? X equals to mk plus d into u, and here we can c bar k into du. So we got b bar equals to m inverse b, a bar equals to m inverse am, and c bar equals to cm. Now here point has come, the how to get the values of m. The m we call as a model matrix, and here the one important thing that the m inverse am and this a must have same eigenvalues. Now we want to determine the values of m. So what we can do, we will assume m1, m2, m3, mn be the corresponding is corresponding to eigenvalues of lambda 1, lambda 2, lambda 3 up to lambda n. Here we are saying that lambda 1 is eigenvalue, and corresponding to this eigenvectors are m1, corresponding to lambda 2 eigenvectors are m2, similarly corresponding to lambda n eigenvectors are mn. Now we can write down the equation as a into m. So a is a matrix operated on vector m, model matrix, so we can write down as a. So m involved eigenvectors m1, m2 up to mn, so we can write down as m1, m2, this process is repeated, and mn. So now we multiplied a m1, a m2, a mn. Now we have seen that Ax equals to lambda x. Now this equation we can also write down in terms of lambda, in terms of eigenvalues. So we can write down as lambda 1 into m1, lambda 2 into m2 equals to lambda n into mn, and this can be written in terms of a bar m, and here this a bar equals to m inverse am, and m is the model matrix, and this m can be written as m1, m2 up to mn. So a and this a bar has same cast equations, their eigenvalues are same, therefore there cannot be change in the properties, but here one thing has been observed, that a bar which will come, that we can get in a diagonal form. Diagonal form is only few elements are present, remaining elements are 0. Now the problem will come that how to calculate the eigenvectors, and you will find that the calculation of eigenvectors sometimes is difficult, but it is observed that if your original matrix A, it is some specific form, so we can easily determine the eigenvector of this matrix. That means if you have a system which is represented by x dot equal to ax plus bu, y equal to cx plus du, and this A, it has some specific form, that is 0 1 0, say 0 0 1, then here minus a3 minus a2 minus a1. So we have seen this type of form earlier. This is called controllable canonical form, or we can say as companion form or phase variable form. So, if you have A in this form and if you want the model matrix M, so the how to get it, because finally we want to achieve this M inverse A into M, this we want, and this M, to calculate the M, that is the eigenvectors are required. So, to calculate the eigenvectors for A, we have to calculate eigenvalues, and for respect to all eigenvalues we have to calculate eigenvector. But if the given matrix is in this particular form, then we can easily write down the eigenvectors. So, how to write down? So, in that case, if the given matrix is like this, so model matrix M we can write down as, so let us say this third order, so we can write down 1 1 1. First row we write down as 1 1 1. If nth order we can write down 1 1 up to n. Now the second row, so we can write down as eigenvalues are lambda 1, lambda 2 and lambda 3. And now about third, it is lambda 1 square, lambda 2 square, lambda 3 square. This is the model matrix, no need to calculate actual eigenvectors. So this M, this matrix is called basically Vander Monde matrix. So if you know M, we can calculate M inverse, then multiply it by A into M, we will get A bar. Suppose if your matrix it is in generalized form, so A equal to say 0 1 0 0 0 0 0 1 0 0 0 0 0 0 0 1, and lastly let us say minus a n minus a of n minus 1 a n minus 2 up to say, let us say the eigenvalues of A, eigenvalues of A, if it is written as lambda 1 lambda 2 up to lambda n, eigenvalues has been written as lambda 1 lambda 2 lambda n. In that case the model matrix M, it is written as 1 1 1, then we have to write down the eigenvalues are lambda 1 lambda 2 lambda n, then lambda 1 square lambda 2 square lambda n square, and at the end we can write down as lambda 1 n minus 1 lambda 2 n minus 1 up to lambda n n minus 1. And so corresponding to lambda 1 this is the eigenvector, corresponding to lambda 2 this is the eigenvector, and corresponding to lambda n this is the eigenvector, and as told earlier this is called as Vander Monde matrix. Now about the another point, invariance of eigenvalues. Eigenvalues under linear transformation cannot change. Already we have seen that we have given system matrix, we have converted to another form. Now we will see also in another way that the eigenvalues cannot change if you use the concept of transformations. Now our problem is we have lambda I minus a and lambda I minus M inverse AM, and our problem is that both are same, both are same. Now how will you prove it? So for that purpose we will write lambda I minus M inverse AM equal to, now this I identity matrix we can write this I as M inverse M. So here we can write down as lambda M inverse M minus M inverse AM. Now what we will do here, we have lambda is there, M inverse M, so M inverse M in the both ways, here it is this side and this side, so we can take it M inverse one side, M other side. So we can write down this equation as M inverse lambda I minus A into M, then this complete determinant, so we can write down as M inverse lambda I minus A into M, and afterward we can write down this as M inverse M to lambda I minus A, and therefore, this is as M inverse M to lambda I minus A, that equal to lambda I minus A. So, here lambda I M inverse M is same as lambda I minus A. That means, you will find that the eigenvalues under transformation cannot change. If you do it, we solve some this example, you will find that A, let us say this A matrix, then you take this M inverse AM, that is A bar equals to M inverse AM, we will get same eigenvalues lambda 1, lambda minus 2, minus 3. Now, the problem is there, if original system has eigenvalue minus 4, minus 2, 3, minus 2, minus 3, then we have come a different form. What advantage we are getting here? Because same eigenvalues, what is the issue here? But you will find that if you have a matrix A, we have minus 1, minus 2, minus 3. That means, it is certain type of decoupling effect you can easily observe. So, now the details of this we will see later afterward, but now here we have shown that by doing some transformations, the eigenvalue cannot change, and we have original matrix A and we get different another matrix A, that we have got same eigenvalues, only thing that we have to do some more calculations. Okay, now we start solving one example. Let us say this A equal to 0, 1, minus 2, minus 3, x, 0, 1 u, and y equal to 1, 0 x. Now, here we have to use the concept of diagonalizations, and we have to determine the model matrix as well as the diagonal matrix. Now, we start doing it. Now, the first step, we have to determine lambda I minus A. So, that is given as lambda 0, 0 lambda minus 0, 1, minus 2, minus 3, and after solving we will get lambda minus 1, 2, minus 1, minus 1, 2, and here lambda plus 3. Now, the determinant of this lambda minus A, that is lambda square plus 3 lambda plus 2 equal to 0. So, we will get the lambda 1 equals to minus 1, lambda 2 equals to minus 2. Now, we have got 2 eigenvalues. Now, our purpose is to calculate the eigenvectors. We have seen earlier that if you have systematic in some different form, we can easily write down the eigenvectors. So, you will find that in this particular matrix A, this matrix is belong to a companion form, or we call as controllable canonical forms. Let us see here 0, 1, minus 2, minus 3. So, now we can to calculate eigenvectors, but there is no need to calculate eigenvector, because if this matrix in this form, we can directly write down a Vander Monde matrix. Therefore, the Vander Monde matrix is say MV model matrix. Here we started with 1, 1, and what are the eigenvalues? Minus 1 or minus 2. Just see here. Earlier we have seen this concept 1, 1, lambda 1 minus lambda 2 minus lambda 3, lambda 1 square, lambda 2, lambda 3 square, but here order is, but in our example order is 2. So, here 1 minus 1, 1 minus 2. Afterward, we have to calculate the MV in, that is inverse of the model matrix. Now, how to get the inverse of this model matrix? So, the concept says MV divided by the determinant of MV. And what is adjoining of MV? That is equals to cofactor of MV transpose divided by determinant of MV. Now, what is the cofactor of MV? Here is minus 2, 1, then here we will get 1, and here we will get minus 1, this is transpose, and divided by determinant of this, So, determinant of this will get it minus 1. So, we can write down as this as minus 2, minus 1, 1, 1 divided by minus 1, and finally, we can get this result as 2, 1, minus 1, minus 1. So, we have got MV inverse. Now, the next step what we want? We want MV inverse A into MV, this we want. Now, this MV inverse A into MV. So, what is MV? So, MV is 2, 1, minus 1, minus 1. We can check it again here, okay, 2, 1, minus 1, minus 1. Then what is A matrix? A matrix we can check it 0, 1, minus 2, minus 3. So, we can write down as 0, 1, minus 2, minus 3. And what is value of MV? MV is 1, 1, minus 1, minus 2. So, we can write down as 1, 1, minus 1, minus 2. We have to solve it. So, first of all we solve this and then multiplied by this. So, we can get 2, 1, minus 1, minus 1. So, here 0 multiplied by 1, 1 multiplied by minus 1. So, we will get minus 1. Then 0 multiplied 1, so 1 multiplied by minus 2. So, we will get minus 2. Then here minus 2 multiplied by 1, minus 3 multiplied by minus 1. So, we will get it as, so you will get minus 2 multiplied by 1, minus 3, we will get it as 1. And here minus 2 multiplied by 1, minus 2 plus 6, this will get 4. So, 1 minus 2, 1, 4. Now, again we cross multiply it. So, 2 multiplied by minus 1 and 1 multiplied by 1. So, we will get it as minus 1. Then 2 multiplied by minus 2, minus 4, 1 multiplied by 4 plus 4, so we get 0. Then here minus 1 multiplied by minus 1 will get 1, and this minus 1 multiplied by 1 minus 1, so plus 1 minus 1 will get 0. And similarly here minus 1 multiplied by 2, 2, and here minus 4, that is 2 minus 4 we get as minus 2. Here MV inverse A, MV. Now, this is called a diagonal form, and we will find that the whatever the values here, they are the eigenvalues of the matrix or eigenvalues of this A bar, and these are also the eigenvalues of this A matrix. Now, these are some references, and as I told you that this diagonalization, although we will find in a mathematical way, but it is widely used in applications, particularly controllability, observability, also a control design. So, we will see later on how this is useful in checking controllability, observability, and also in controller design. Thank you.